Tonight on Revolutionaries.
It's not a random walk. I mean, we're very disciplined in choosing where to work.
Our look behind the scenes of Silicon Valley's great research labs continues in tonight's Revolutionaries with Intel Senior Fellow Dr. Justin Rattner. Justin talks about his 40-year career at Intel and in particular his 2 decades of work with the legendary cosmologist Dr. Stephen Hawking. Major funding for Revolutionaries is provided by the Intel Corporation.
Does it seem like it's been a long time that you've been doing what you've been doing, or has this gone by in the blink of an eye?
You know, it's blink of an eye.
Yeah.
I mean, and it's hard to believe that 40 years ago, I was sitting down with Shima-san, trying to get the flag settings for the 8080, which was about to launch. I guess about a month and a half after I got to Intel. It seems like only yesterday.
What was it, when you look back at the very, very beginning, what was it that caused that voice inside of you to say, you know, this part of technology is of interest to me. I want to be an engineer. I want to pursue something in pretty early days, certainly when nothing was like it is today.
Well, I know I drove my parents crazy.
Yeah.
Because, they would give me some new toy. Probably my favorite example is, I got a little, locomotive, and within a matter of a few weeks, I had deconstructed it, I think is the operative term these days, right?
You know who else did that? Charles Babbage.
Well, there you go.
Babbage was famous for deconstructing his toys.
I'm in good company then. So, I had this habit of taking things apart and on rare occasions actually reassembling them. But, I was always interested in how things work. And that led me into being an avid electronics hobbyist. Today I would be called a maker. We didn't know what makers were in those days, and used to build kits of all kinds, and eventually built. I think I was about 12. Built a simple digital device with a few flip-flops, and took it to junior high school science fair, and had all the teachers wondering if my dad had built this thing for me. And my dad, they actually called him at work, and he said, no, he says, I just write the checks. I have no idea what he's doing. That's all him. So
was he technical?
No, he was not technical at all. And then that's why they found it so hard to believe. And they literally cross-examined me. I mean, do you have an uncle, a relative? Do you know somebody in the electronics industry? No, I just like doing this stuff.
It just spoke to you.
Yeah. So, so then, I mean, in, junior high and high, finally getting to take science classes and having the opportunity to get a more formal grounding in all of this.
What about a mentor or a teacher or professor somewhere along the way that really said, Justin, you've got a real talent for this?
No, I think if you want to think about it early, but not a mentor, but I think somebody inspired me. I was taking a summer science class, and through the LA City School District, and we went out to Hughes Research Lab. If you've ever seen it or been there, it's just incredible, up on the cliffs overlooking Malibu. And one of our hosts was Ted Maiman, and they had just gotten the Ruby laser working. Oh. And we were just, oh my God. And they had it all nicely packaged and everything, and they showed us where they were, pulling the crystal and all of the stuff to make the rubies and all of that. So that was a tremendous source of inspiration. I mean, that was the one and only time I met Ted Maiman. But literally, when I applied for college, I applied in applied physics. But that's when the story takes a decided turn. So. In LA, you can graduate either in the winter or in the summer. And so I was a winter graduate. I had nothing to do until the fall to go to college. And a buddy of mine who was at MIT, but from the LA area, said, "Oh, they're hiring at Scientific Data Systems." And think about connections. This is Max Palevsky's company, who later becomes a major investor in Intel. And so I went to work out there. I passed this little transistor theory test, and you're hired. And I'm working in board test, and they have an automated tester, just one on the whole floor. And none of the techs wanted to touch this thing. And I got some instruction, took home the manual, and I'm cranking out boards at 10x what the rest of the techs. So they were ready to get rid of me because I was shifting the curve. So I got moved out to system test, and and here I am. I've got 2 or 3 of these SDS 930s just sitting, on the floor, and I had taken a programming class. So for the rest of the summer, I just brought these machines up and ran them through all their diagnostics and had the freedom to program them, any way I want. Needless to say, when I got to college, to Cornell, I said, okay, I'm not doing applied physics anymore. I said I want to do computing, and switched into electrical engineering, and the rest, as they say, is history.
Yeah. So you joined Intel in 1973 after some time with HP and Xerox. What was it like at that point, and what took you there?
Yeah, well, the interesting thing about how I got there, I was working at HP in the mini computer division, off of Wolf Road down there in Cupertino. And a buddy of mine from HP was a compiler guy, had already gone to work for Intel, and he said, "Hey, you ought to come over and interview. It's pretty neat. We're doing some interesting things." But one day I just happened to be walking by one of the mechanical engineers' desks, and he was working on a VT100 class terminal, and I started talking to him about it, and he showed me the motherboard, and he's saying, he says, this is the Intel microprocessor. Pretty sure it was an 8008, and which was sort of built for doing, those old terminals. And I said, well, what do you think about that? Because at the time, we were doing everything with, TTL, whatever. And he goes, that's the future.
That processor.
That you just pointed at the 8008 and said, that's the future. And I said, when the mechanical engineer is pointing at a chip and telling you that's the future, that's something to really pay attention to. Now, this was my own private theory for many, many years. But at a supercomputer meeting in Kissimmee, Florida, Seymour Cray is giving a keynote presentation and relates the story that the only engineer he took with him from control data to Cray Research was his mechanical engineer. So Cray and I shared that appreciation for mechanical engineers. So it was just that remark, and I called my buddy at Intel and got an interview set up, and got to interview with Ted Hoff and Stan Mazer and and the whole crew at Intel at the time, and it was clearly the important opportunity.
Still a small company at that point.
Oh, it's still a very small company. I mean, Bob and Gordon, were just upstairs and shared an office, and yeah.
Was it clear?
I should have asked for more stock in that initial offer as I think of it. I actually asked my dad, what he thought about the offer, and he says, go in and ask for more money. I could have gotten a lot more stock than money, I think, if I had asked for stock.
So what were their immediate needs? What were the things a young engineer, very bright like you, was most needed to do?
Well, there just weren't very many computer people at the time. Bill Davidow had just taken over the microprocessor group, whatever it was. I can't remember exactly what it was called at the time. And I mean, we were really starving for computer savvy people. I mean, most everybody was semiconductor technologists in some manner or fashion, and so they were just starting to build a team that that really had the computer experience. Like I said, I sat there with Shima-san, because I was basically trying to complete the 8080 instruction set definition so it could be published and delivered to customers. And nobody knew what the flag settings, how each instruction set the flags. And they said, well, go ask Shima-san. So I go upstairs, and I knew I was in trouble because he reached into his print stand, pulled out the schematic of the 8080, rolled it out on his desk and said, give me the opcode, I'll give you the flag settings. And that's the way we went through the instruction set. So I'm not sure they were actually architected, if I can use that term. I think, the flags got set basically the way the logic worked out. And sometimes people, I would be in customer meetings and people would say, why do you set the flags that way? Because they didn't always make complete sense.
Was it the difference between understanding computing at a system level and then understanding it at a chip level? Is that sort of what was needed?
Yeah, and and there were, it was a very innovative environment, and I give a lot of credit to Terry Opendijk, who ran the software team, and to Gary Kildall, who got Intel to do things, like the PLM programming language, and and there were lots of debates about, whether or not to do an operating system, and how sophisticated it should be, and all those kinds of things. So, I think it was really valuable that that very early on, they, the management team recognized the need to bring in computing people. We weren't making any money in microprocessors. In fact, it was years, I think, before Intel made money in microprocessors. But what we lost in microprocessors, we made up in memory. So it was a viable business.
Now, I've always heard it described in the early days as being a very innovative environment. It's just what you said. What made it innovative as a culture and a place to work?
Wow. I really can't say enough about Bob Noyce. A force of nature. And, I remember sitting in my office, and those were the days of closed-door offices at Intel before we went to cubes, and, there's a knock on the door, and, Bob walks in, and there was another desk in the office, but there was nobody at the desk, and Bob hops up on the desk, and we just, chatted about things, microprocessor things for the next hour, so. And, it was just thrilling to be able to, share in that brilliance. I mean, he's just such an extraordinary individual, and a great loss. I mean, he died too young. But, a true innovator, entrepreneur, all of that. Everything they say about Bob is true, and then some.
And so the path into research was sparked by what for you?
Well, I think...
and labs and experimentation.
Well, yeah, I think, the early supercomputers, certainly, these early parallel machines, were to some extent experimental machines. We barely knew how to program them, and so there was this constant sense of discovery that that was going on, discovery on our own and discovery with our customers, who were, these were some of the leading research institutions here in the U.S. and elsewhere around the world. So, we were in some sense sort of immersed in a research environment, even though our principal mission was supplying tools to researchers. So, when it was time for me to move on, it just seemed like the natural thing would be to continue in that research vein. And I went on. I founded the server lab at Intel, and that was just sort of the first step in that whole scenario.
What was the early grail in high performance computing that you found yourself chasing with the research agenda?
Well, Yeah, at first we had to convince people with money that this idea of lashing up a lot of microprocessors was actually the path, not a path, the path to high-performance computing. I remember going to a conference, I think it was in upstate New York somewhere, Albany or Rochester or something, and I think I was the only person who spoke about what later became known as the attack of the killer micros. I think that was a few years later. But I mean,
what did that mean?
Well, at the time, everybody was, buying these big machines from, principally from Cray, but, Control Data had its machines, and there were others out there, ETA and so forth. And so big vector, custom hardware machines ruled the roost. And somebody coming in with a lowly microprocessor and saying, well, it's not very fast today, maybe 50 kiloflops, but just give it, a couple of turns of Moore's Law, and, it'll be, 500 kiloflops and then 5 megaflops and, so on and so forth. And, there were not many takers in those days, but I knew the tide had turned. I guess it's 1991, and we put the big Delta machine, which you have in your collection, by the way.
We do. It's right downstairs.
You even have the little monument we built. I've seen it. When we installed the Delta at Caltech, I think it set the parallel LINPACK benchmark record, beat the Cray XMP, if memory serves. And I don't think a microprocessor-based machine ever lost that, that title again.
After that?
After that, yeah. There may have been somebody, maybe one of the Japanese machines snuck in there somewhere. But.
Did you have to develop the applications to run on these machines in order to convince people you really were on the right path?
Sure.
So what were the early things that you had to do to demonstrate that that was the case?
Well, we had to tackle, all manner of sort of the fundamental arithmetic. How do you turn these, these algorithms, these serial algorithms into parallel algorithms? How do you get them scheduled? How do you get them communicating? It just was, everything and anything. There was not much, how should I say, off-the-shelf knowledge available. So, we went out and we hired people like Cleve Moeller, from MathWorks. MathWorks was a little company in those days, and even though Cleve founded it, Cleve needed a job. So, Cleve went to work for us and put together, I think, a first-rate team of computational scientists. I think we called them numerical analysts at the time, but computational scientists and algorithmic experts and so forth, and began again working very closely with our customers, teams like at Argonne National Labs and elsewhere to really build that early base of know-how.
If customers were hard to convince in the beginning, which you said they were, what was the tipping point? When did it finally cross that point?
Well, I think
for your app.
Yeah, I think I don't know if I could pick the date off, but it's probably, I would say it's probably in that in the early '90s when the big parallel machines just, their peak performance is just leaving the vector machines in the dust, and there were still incredibly heated arguments. I remember, actually, we're just a hop, skip, and a jump from NASA Ames, and they were very proud of the Crays that they had, and I used to get lectured about, there's all this parallel performance, but we can't get to it. It's too hard to program. Another one of the criticisms was, yes, you can get an algorithm to run very efficiently. You can get very high degrees of concurrency, but the algorithm itself is not very efficient compared to things that we'd run on these vector machines that just would be horrifically inefficient on the parallel machines. But that lure of what was then 100 gigaflops, and then by the mid-90s, a teraflop, just continued to attract more and more interest from the community.
Has this always been the Everest of computing, if you will, this absolute pursuit of speed and calculations per second and so on?
Oh, absolutely. Yeah. In fact, I can't recall who said it to me, but the line was very simple: fast enough never is. And I mean, I think that's still true today. That there are problem classes out there, beyond maybe the tens of petaflops we can do today, and that's why there's so much conversation going on about how do we get to exaflop machines and even beyond that. I think the problem has clearly changed from how do you wire these things together in some efficient form to how do you power them. And a few years ago I was on a DOE panel, and we were going around, everybody was giving a brief presentation, and I said, well, the three challenges for exascale computing are power, power, and power. Everything else is sort of down the line a bit. So power has become this huge challenge for these high performance machines, and nobody in the industry wants to be supplying a nuclear reactor with every one of these guys. So I remember talking to Secretary Chu a few years ago, and we were talking about the 20 megawatt target for exascale, and he's saying, well, I think it should be 10 megawatts, not 20 megawatts. And I'm going, getting to 20 is going to be an incredible challenge. And now here's the Secretary of Energy saying it really should be 10. And I couldn't sit here today. I don't know if anybody could sit here today and tell you how you get to even 20, but before the end of the decade. It's an enormous challenge.
Just in layman's terms, can you explain how much power 20 megawatts is? What would we be powering if we had 20 megawatts of power?
It's probably a small city or something like that. That's 20 megawatts is a lot of power. Part of this is, and in fact, the cloud data centers are already up against. They can't pull enough off the local grid to put all the servers they'd like to put into a single data center. So they're starting to cluster the data center and the data centers, and the high performance computing people face the same problem. They literally cannot bring enough power into a single facility to power some of these machines.
So you built a machine or a system for the Department of Energy that achieved teraflop performance, which is 1 trillion operations per second. For those of us who didn't memorize our table of 2 to the x power, what is an exaflop?
Let's say 10 to the 12th.
Yeah.
Oh, exa.
Yeah.
Oh gosh, 10 to the 18th.
10 to the 18th.
Yeah. Did I get that right?
Okay.
I'm not often asked to do math on stage.
How far away? See, I have notes. I'm cheating. You're sitting there with nothing.
It's easy for you.
I've got this all written down here. I'll show
I gave my calculator
You can
away.
cheat off my piece of paper here if you like. What application will get cracked at the time that high performance computing achieves that level of sophistication?
Virtually every scientific discipline in that DOE panel I mentioned, we brought in all of the scientists, chemists and physicists and, biologists and all this stuff. And they could all talk about the kinds of problems that they would solve with that much performance. And so I don't really think there's any argument that it's in our competitive interest as a nation to have that kind of computing capability. And we're simply not going to be competitive if we let others around the world either have access to these machines or let them build these machines with their own technology. If we could just say, hey, as far as we can see, this is going to remain an economic necessity, competitive necessity. If we just get everybody on that page, then I think we wouldn't have the struggle with every one of these jumps in performance that we do. But we're clearly not there yet, and people on the Hill are still looking for, well, give me the national defense, the strategic argument why we need to build one of these things, and it's just getting harder and harder to do that.
Let's leave high performance computing for just a minute and talk about Moore's Law, which we were talking about earlier. So no conversation with an Intel senior fellow would be complete without a discussion of Moore's Law.
Right.
Where do we stand now on Moore's Law and how it's going to play out?
Okay, before I answer, you need to provide me with a little more definition as to what you think Moore's Law describes, and not the typical explanation, because if Moore's Law in some sense is independent of the underlying technology, then then I think Moore's Law is very likely to last for many decades into the future. If Moore's Law pertains to a specific technology, we've actually seen those technologies ride on Moore's Law come to an end. For Intel, Moore's Law for silicon gate MOS technology, ended, 3 generations back, right? And a new set of materials, high K metal gate, had to replace silicon gate because the oxides were getting too thin, and the leakage was dominating the power equations. But there was plenty of opportunity for innovation, and and a replacement material stack was developed and brought to market on the 2-year cadence of Moore's Law. And I don't think the significance of that was really brought to wide attention. That hey, some version of Moore's Law, some instance of Moore's Law did come to an end for silicon gate, and and a new version of Moore's Law. By the way, the new version of Moore's Law didn't last very long either, because I think it was 2 generations. We introduced the Tri-Gate, the FinFET transistor, and now we've changed the material stack and we've changed the physical structure of the device. And and I think we're in a period. In fact, I was teasing one of the material guys at Intel a few years ago. I said, "Oh, you guys have really come back into fashion. Just making better silicon or nitride or oxide, whatever it is. That's what these guys did for their bread and butter. But now they're back to the periodic table, going, oh, okay, something from this column ought to work out. Okay."
I'm going to talk now a little bit about your relationship to Stephen Hawking and this search for an interface that will allow him to be open to the world and us to be able to understand him. Let's start, if we will. Well, let me set the stage for the video clip that we're going to show, because Stephen contracted Lou Gehrig's disease at the age of 21, and he's just celebrated his 70th birthday. 71st birthday, which is absolutely amazing. Right. And You were part of the celebration of the birthday, and we're going to show a little piece of video, and then we're going to talk about your work with Stephen Hawking.
Today marks a very special day in history, not only for Stephen Hawking, but also for many, many people and lives that he's touched throughout his time. Many people gathered at Cambridge University here today to celebrate the life and the work of Professor Stephen Hawking and the impact that he's made.
Dear fellow friends of Professor Hawking, we're sure that you agree that Stephen has done more to promote the public understanding of cosmology than any other living individual. And we are glad to consider this remarkable man our friend. There is no more appropriate time to honor Stephen than today, his 70th birthday.
It's really an honor for me to be here on this very special occasion, and we're just just delighted to be part of this great celebration for Stephen on the occasion of his 70th.
Now that I have reached 70 years and 10, I hope you will forgive me for looking back over my life and how our understanding of the state of the universe has changed. I was born on January 8, 1942, exactly 300 years after the death of Galileo. However, I estimate that about 200,000 other babies were also born that day.
We're going to be looking very carefully at applying some state-of-the-art computing technology to improving Stephen's communications speed. We hope that this team has a breakthrough and actually identifies the technique, and we can get Stephen communicating back at the levels he had a few years ago.
That's fantastic. So talk a little bit about what the challenges are and what you're working on with him.
Well, Stephen got a hold of me, I guess it was October of 2011, and just sent me an email. You're just sort of browsing through your emails, and all of a sudden Stephen Hawking, scrolls by, and you go, whoa, and typically, it's like, it's somebody selling a book or something like that. This is really Stephen Hawking, and seemed to have the right credentials and all of that stuff. And he invited me to to come to Cambridge and have this conversation about what we might do to bring his communications performance back to the level it was a few years ago. I mean, he was doing 10 words per minute, then it dropped to about 7 words per minute. And now I haven't seen a recent number, but my guess is it's sort of in the 1 or 2 words per minute. And I mean, Stephen's not verbose, but when you hear a lecture like you heard in the clip, and that takes a lot of time for him to craft. Even just having a question and answer session with Stephen, as you ask the question and then you take a break, and maybe 10 or 15 minutes later you get a few word answer. I hope you could all see it was pretty sharp here on the down monitors, but his current interface is just this blink sensor, as we call it, that is hung off his eyeglasses.
It dangles down near his cheekbone.
Yeah.
It's a sensor.
Yeah, and the reason it is because when he blinks that eye, you get a little signal, and we amplify that signal, and eventually what that does, his classic interface is it stops a cursor, and the cursor is traversing the screen where the letters of the alphabet, other symbols, numbers, what have you, and then a small number of, computer commands are located. And what Stephen does is wait for that cursor to get to the letter or symbol or command that he wants, and he blinks. And if he's got to make a correction, he has to wait for delete to come by and choose delete, and then he's got to go back to the letter. And I mean, you just think about this for a while, and you realize how tedious this is. That said, he's been remarkably successful using it. He's surprisingly good at it. I mean, we've had other people try to, to do it, and it ain't easy. And, they inevitably wind up either, blinking too soon or too late. But, he can do it pretty reliably. So it was during that first conversation that I noticed he was communicating with members of his staff using facial gestures. And, we started to talk about that as well. If really those are distinct gestures, we can probably train a computer to recognize those and expand, his symbol set beyond this, this one blink, which is, pretty limited. I said, gee, if we could just distinguish between a dot and a dash, we'd have Morse code, and, that would be a big improvement over where we are. So it was at lunch when I think his personal assistant is Judith. Judith comes up to me in the lunch line and she goes, he's got a lot more expressions than the kids realize. Huh. She's been his assistant for many, many years, and and I mean, she just looks at him and she knows what he wants. And so I said, okay, I believe that, and if that's true, we can teach a computer to recognize those expressions. Then we were ready to send one of our research teams in right away. Stephen was ill. Actually, Stephen was ill at the 70th birthday. He did not attend in person, although he did give his lecture. So I think it was probably February of 2012 or a bit later. The team, finally got to spend time with him, and he gave them hours and hours of time. And I think a lot of credit, both to Stephen and to the team. It was framed as a research project. We're not here with an answer. I think that may have been why he rejected some of these other technologies that people had brought to him, because they had a solution and they were trying to make it fit, and we were looking for a solution, and we laid out a series of experiments, which he was a key member, and he gave us an incredible amount of time, and I mean we captured that stereographic, multiple cameras and all kinds of stuff, and then we set to work to redesign the user interface, which is more than a decade old. He hasn't switched to the new interface. I want to be very clear on that. But he uses it, and he also comes in via Skype using the interface to the labs here in Santa Clara, and run Skype, using the new UI. So we're still tuning and honing and optimizing, and we hope by the end of the year that we'll be ready and he'll be ready, and we'll make the switch to the new interface. But anybody who's worked on the team will tell you he's just been a delight. We have high hopes for a successful transition to the new UI.
This is a great segue into contextual computing, and let's talk about that for a minute before I get to the audience questions.
Sure.
Talk about that as a next frontier in computing and the research that you've been doing and your team has been working on.
Well, yeah, we've been working on context for a number of years now. I think my view has been for a long time that that's the next major advance. When we look at different applications for context awareness, they lift almost everything to a level where you think you're dealing with a conscious entity. I don't want to get too carried away with that, but when you bring context in to, to almost anything, I mean, you begin to feel like, well, there must be a sentient being here running around someplace, because suddenly, dialogues of almost any kind have this very human feel to them. I remember we were doing speech research at our Beijing lab, and this was shortly after I took over microprocessor research. This is 2000, and I had this phone call, and I'm talking to the research team there, and the whole lab in those days was doing speech and natural language, and I asked one very simple question. I said, "What's the relationship between recognition performance, recognition accuracy, and microprocessor performance?" There's this long silence, to the point I'm going, maybe we've lost the connection. And finally somebody says, "Well, there isn't one." And I said, "Well, if that's true, we're in big trouble." It was a recognition, at least at the time, this is 13, 14 years ago, it was a recognition at the time that the algorithmic know-how simply wasn't there to exploit the performance. So just throwing more MIPS or flops at it wasn't going to improve accuracy. So, when you start to bring context to bear, let's say, in speech recognition, as Victor Zhu described it, you go from things that feel stupid to things that begin to feel very familiar, and they had this system at the time, I guess, where you could make a plane reservation, and I don't recall exactly how you got to this thing, but you could call up and make a plane reservation. Well, God forbid you got halfway through the reservation and wanted to change like the time of departure, and you would say, it would say, well, it would prompt you, it would say, I have departures from Boston to Washington at 8, 9, and 10, and you would go 10. And it would go, okay, I booked you for a 10 o'clock departure. And then you'd say, no, I really want to go at 9. And then it would go, I did not understand, the previous utterance or something. And it would go, well, I want to take the earlier flight. Well, at that point, it's completely lost. And, context, gives you the ability to, recognize that you're in a conversation about air travel, and that corrections are a natural part of making a booking. As I said in my IDF keynote a few years ago on context, there are also platform implications of context, and those are going to be very important because as you begin to introduce context, now you need to literally be always aware of what's going on. I mean, you need to be processing sensor input on a continuous basis. Well, that requires innovation at the platform level. I mean, why do you think you have to push the button on so many of the recognizers we have today to say something? It's because it's too expensive just to listen all the time.
Yeah.
Right? And we've got to get beyond that, right? I mean, I don't push your button to, have you, listen to me. We've been working not only on these sort of higher level machine learning algorithms for bringing context to bear, but also on how do you change the platform so that it has the appearance of doing continuous sensing in multiple modalities, and again seems to exhibit human-like behavior.
Before we get to the audience questions, I just want to take that last answer that you gave as an example of something that really fascinates me with your labs and with every lab we've explored, which is that there seems to be no boundary. You've talked about things that I'll bet if people in this audience who are listening or people on the radio who are listening thought about Intel as a company, many of the things that you're talking about are not necessarily something we would associate with Intel the way we know it. And that's true of many labs. What has it been about the culture that you've built and you've experienced that has created this sense of freedom that we're just going to wander through the world and we're going to encounter all these human problems and we're going to pick some interesting ones and really go deep?
I think we've understood for a long time at Intel that our future isn't solely dependent on the next better transistor, and as soon as you sort of realize that the products of tomorrow are going to depend on a range of technologies that go way beyond just what that transistor is doing or is going to do in the future. You almost can't. Where do you stop, right? Why do we have a team of social scientists, anthropologists, at Intel Labs? Well, understanding how people experience technology informs much of what you're doing. I mean, when you're trying to decide between a set of product features, why not focus on the ones that dramatically enhance the experience as opposed to ones that hardly move the needle at all, right? They're just somebody's, I'm really good at doing this. So, that's when I'm going to put in the new thing, whatever the new thing is. And everything in between. You said something that I want to make sure, the audience, doesn't misunderstand. We do cover a huge range of technologies, but it's not a random walk. I mean, we're very disciplined in choosing where to work, and we go through a rather rigorous process, typically in the late summer, where folks from the labs and folks from the business units at Intel, meet together to learn from one another. What's coming on the competitive side? That's what the product people are so good at. What's coming, in terms of technology? What can or we can't do, or what's hot or what's not? And we literally build priority lists. I mean, top 10 or top 40, I guess. It turns out at any instant we have about 50 joint projects between the lab and the business unit, again, that cover this huge range. But, they're not chosen because, the lab just said, okay, here's what you get. And they're not chosen because the business unit says, well, this is what I want. I mean, we work collaboratively to hone that list. Now, we also, and I tout this as sort of a rule of thumb, even though it confuses some of my colleagues at Intel. We spend half of every research dollar doing things that are directly related to what the business units are doing. Technologies that will enter their product pipelines in the businesses they're in. The other half we spend on exploratory work where we don't necessarily have a product intercept in mind. One of those technologies is silicon photonics. When we started, we couldn't give away that technology, but we had a belief that it would ultimately yield an incredibly important advance in optical communications, and would ultimately find a home in our product. So, I believe quite firmly you have to do both of those things.
There are all new experiments being tried now with the interface between humans and machines. What are you seeing now that you think is really a breakthrough or a major step forward in the way that we do deal with that interface with all these machines that surround us and are going to surround us even further?
Well, I think this notion of personal assistance, of much more anticipatory kinds of behaviors from our various devices. I mean, I've talked about this at the Intel Developer Forum. Genevieve talked about it. Genevieve Bell talked about it at the recent IDF. This fusion hard sensing and soft sensing. I can't say enough, about how critical that is and how critical the machine intelligence functions are to successfully fusing hard and soft sensing. Your calendar is a wonderful sensor. It knows as well as anyone, well, maybe short of your administrative assistant, where you are and what you're doing. And, and that can be harnessed and brought to bear on, providing you a set of functions and services on your various devices that suddenly display a surprising degree of understanding of who you are and what you do. I think that's the potential for context. When you get in your car should know all of those things, right? When you watch television, we see bits and pieces of it, recommendations and things like that. But there's so much more to it, and I won't even tackle, unless you throw that question at me, the privacy implications of it all. But if we can figure out how to truly secure that information, I think that will be, for us as individuals, some of the most important information that exists for us on the planet.
I want to close with asking you the question that we classically answer every revolutionary who comes to this evening, which is, if you were going to give a young person just starting out, a young engineer, or someone like the young women we were talking about, interested in math or science or engineering today, some advice, and I know you're called upon to do this all the time, what advice would you give them?
You have to be fearless. You have to have, in fact, I just did this at the Grace Hopper Women in Computing Conference. You have to be fearless. You have to have a vision, right? You have to have something, that will change the world if you're successful. People come to me, from time to time, more often than not, and ask for career advice, of some sort. And I'll simply say, well, what's your agenda? What do you want to do? How do you want to change the world? Tell me that. And then we can have, a conversation about your career. I think too many people are sort of willing, and it may be actually symptomatic of the way our educational system works. People are much more comfortable being told, well, this year you'll take the 300 level classes and next year you'll take the 400 level classes. I think the real innovators in the world never thought about, gee, could they get into the 400 level class, or, did they have to do the 300s before the 400s? That's being fearless and spending a lot of time thinking about what you want to do and make that your agenda, and then go forward with the confidence that, with that vision and that focus, you can be successful.
Justin Rattner, thank you so much for being here tonight. It's been a great conversation. Appreciate it. Thank you.
Intel's research with Dr. Stephen Hawking may help the revolutionary scientist continue to communicate his ideas with the world. There are hundreds of stories like this at the Computer History Museum. Join us next time for the Computer History Museum presents Revolutionaries.